If you take systems like these and just let them run, this is what happens. They wobble and crash, drift and fall over, and sometimes they fail in a very spectacular way. Each of these systems is unstable, and without control we can't cheat the underlying physics, and that obviously doesn't end well. Let's rewind that. Same systems, same physics, the only thing changed is the software running on the controller. Now the Segway stays upright, the beam balances, and the rocket not only takes off without any hiccups, we even manage to land it again. They still want to fall over, we just don't let them. So the real question isn't whether control matters, the real question is how we do it properly. What exactly do we change, and how many different control concepts do we need for that? Here's the surprising part. We can stabilize all of these systems using the same underlying idea. Not 3 different ones, just one. This idea is called state feedback control. This video marks the starting point of a new series where we will build a clean and intuitive understanding of what that means. Whether we are stabilizing something that is inherently unstable, or simply reducing oscillations in an otherwise well-behaved system, the core idea stays the same. State feedback is often introduced using very flashy examples. Rockets, segways, the inverted pendulum. They look great and make for nice looking animations like the ones you've just seen, but they don't always make for the best teaching examples. Here's why. Very often, applying a controller to these systems turns into trial and error. Not working, still not. Okay, now it works. In the end, you are left with a controller that stabilizes the system, but without a clear understanding of why it works, or how to apply the same idea to a different problem. So we will take a different approach, because sometimes a system with a few springs just makes for a better explanation. We will start with the theory and talk about what state feedback means in practical terms, and how feeding the state information back to the systems allows such drastic changes. We look at poles and system dynamics, why a single pole at 0 can be acceptable, but 2 already push the system into instability. Only once that foundation is in place will we move on to real systems and design controllers from scratch step by step. If this kind of approach is what you've been missing so far, building the understanding first before touching the controller, then this series is very much for you. We will look at how to choose pole locations systematically, what happens if your model isn't perfect, and how uncertainty and noise affect both performance and stability. And even if you never plan to design a controller yourself, I'm pretty sure you will gain some extremely effective conversation material for the next family gathering. For example, as you can clearly see, 2 poles at 0 imply instability, which follows directly from the Jordan normal form. Bad jokes aside, if you want to follow the rest of the series, make sure you are subscribed. The next video starts exactly where this one ends. Bye for now.